Okay, so we've talked about spectra, and we've discussed how motion, well, I really should capitalize this, but made a mess there. How motion affects the spectra. So spectral lines are shifted one way or the other. This is called the Doppler shift. And now we'll talk about what's called the luminosity-distance relation. So these are really the fundamental tools of astronomy that they allow us to understand what is out there, how it moves, and how far it is. Okay, so let's discuss the luminosity. Let's derive this luminosity-distance relationship. And so we imagine a source, right? So this could be a star, and it's emitting light at various frequencies. We'll look a little bit later at the relationship between the luminosity, the temperature, the wavelengths, and how these things change as the temperature increases. So we imagine light is being generated, electromagnetic radiation. It's moving outwards from the source, here depicted with little wiggly lines. That's the electromagnetic radiation, various frequencies, radial distribution of energy. This is all of that energy together is the luminosity, or L, of the source. And then, so let's consider the energy comes out, and here is a sphere centered on this object. So all of that energy crosses the sphere of some radius, and as we imagine larger spheres centered on the source, that energy eventually reaches those larger spheres, and it's always the same total amount of energy, L. So notice that at one point on these spheres, we have just a fraction of the total L, of the total energy, and the relationship between that fraction, which is we call the flux, involves the total area of that sphere. So there's spheres here, and there's a radial value. It's a variable, right? This R is getting larger and larger, so we're considering spheres of larger and larger radius as the light moves away. The total energy is L, but its relationship to the energy per unit area on these spheres, the energy per unit area is called the flux, or F. Right? We can get that by taking F and multiplying it by the total area of the sphere. So we have 4 pi times r squared. That's the area of a sphere of radius r. So the total luminosity L is related to the flux by the area, by that expression. So we can imagine if we know the L of the source, then, right, so the energy arrives to us on Earth over here, say, here we are, we measure the energy per unit area, that's the flux, and we can then figure out, if we know L, what the distance is. So, right, R becomes the known L divided by 4 pi F square root. Right, so we can get the distance of the source if we know the luminosity. And so the challenge is to figure out the luminosities of objects that are further and further away, so we can understand how far they are. And so this will take us to the notion of a standard candle. Right? Objects whose luminosities we know, their luminosities are all the same, they're standard candles. Objects such as certain kinds of stars that pulsate in a certain way, Cepheid variables, exploding stars that explode all in the same way, they sort of reach a peak luminosity, supernovae. And these kinds of objects, we'll argue, we can find their luminosities, and they're all the same, and therefore if we observe them, we'll get their flux, and we can then get these, given these two known quantities, evaluate how far they are. Okay, so with spectra, again, we can we know what is out there. What is out there with the Doppler shift? We know something about its motion, how it's moving, and now with the distance, luminosity-distance relationship, we can find out how far, the distance of objects. And these are the fundamental tools of astronomy that allow us to understand the universe.